All right, our last speaker of today is Dragomir Saric.
Good.
Yes, of Queen's College. And he will speak about infinite Riemann surfaces, the type problem, quadratic differentials, and Teichmuller spaces.
All right, well, thank you. First, I would like to thank the organizers for inviting me. This is like a great conference. I enjoy all the talks and have fun in Toronto and in the fields. Let me start by maybe saying some definitions. So I'm going to take, we think of a Riemann surface R to be given as a quotient of the maybe hyperbolic plane, upper half plane with the Fuchsian group gamma. And I will say that this Riemann surface is infinite if gamma is not finitely generated. All right, so in general, I'll talk about also Riemann surfaces which are infinite in some other sense, geometric sense. But for now, when I say infinite Riemann surface, I'll really mean that the Folty group is not finitely generated. So these are not compact surfaces. They are not function surfaces. They have more geometry. So I'm going to try to give you like a motivation why I would want to study quadratic differentials on such surfaces. And the first motivation comes from some consideration of the type problem for Riemann surfaces, basically when a Riemann surface is closest to being compact. Infinite Riemann surface is closest to being compact. So the main theorem is the following. So the following are equivalent. So number one for Riemann surface. Number one, R has no Green's function. So sometimes this is in classical notation denoted by R element of the null G class. G is for the green. And sometimes R is called parabolic. All these things mean the same thing. So this condition is equivalent to the statement that the Poincare series for the Fuchsian group gamma diverges. So the sum over all elements gamma of e to the minus the hyperbolic distance of a point z to point gamma of z is infinite for any point z in the upper half plane. So this condition kind of says that the orbit of a point doesn't go to the boundary very fast. Otherwise, this series will converge. So these two are equivalent. And then third condition, geodesic flow is ergodic. Geodesic flow on the unit tangent bundle of the Riemann surface R is ergodic. We're all familiar with that. Number four, Brownian motion is recurrent. Maybe number five, extremal distance. So extremal distance to boundary at infinity of the Riemann surface R is infinite, equals infinity. And there are like, I'm sure if you look at the literature, there are like at least 30 more that you can easily find. They're all equivalent. So the number two, the number three, and the number four is something which is called Hopf-Zurgi-Sullivan theorem. And number one and 5 and all other equivalent things going even further back to the Finnish school, right? To Alfors, Sario, and people around them, Lassonen, and so. Those are all. This is kind of a nice bunch of equivalencies, and that's kind of one motivation. I'm kind of really like that. So looking at number 3 on the ergodicity geodesic flow, there is the immediate first observation is that if gamma is of second kind, then R is not parabolic. Its geodesic flow is not ergodic. That is because, like, if gamma is of the second kind, that means that your surface has a big opening and the geodesic flow will just escape. So it's kind of almost obvious that this surface is not there. So if gamma is of the first kind, then a surface may be parabolic or may not. And that's kind of the sort of the interesting place to look and find the differences between being a parabolic or not being parabolic. But what we do know is that if gamma is of the first kind, that is equivalent to the fact that there exists geodesic Pan's decomposition. Of the Riemann surface R. So you can always break your Riemann surface in geodesic pairs of Pans if gamma is the first kind. Actually, a bit more is known. Basically, what is known that if you take any topological Pan's decomposition, that Pan's decomposition can be made into actual geodesic Pan's decomposition. This is for the hyperbolic metric, right? So any geodesic things that say there will be for hyperbolic metric. So to maybe start thinking of these surfaces, so there is this example which is called the infinite fluid surface. So yes. The limit set. So the limit set has is the Cantor set on the circle. So there are some intervals which are not in the limit set, and that's where you see the geodesic flow escapes to infinity. That's a second kind. First kind limit set is everything. So the second, so this is maybe open, right? So this is not in the limit set. So this is second kind. First kind, the limit set is everything. So you don't see these kind of openings, right? So if you're somewhere in your surface, you can escape with an open angle of geodesics to that point, and that geodesic flow is not ergodic. That's kind of great. So when I was drawing these pictures for Salian and Hiolos insisted that I draw punctures the way they are, which means they're very infinitely far away, and Hiolos insisted that I draw like this. So maybe just once. So they look like this. But then, okay, these are punctures, but they're not so nice. They're not as they're supposed to be. So this surface is called infinite fluid surface. And that's my colleague Arabas Mejian. He's kind of popularized that term and this surface. So basically, Pan's decomposition that we are talking about, geodesic Pan's decomposition is given like this. So the first pair of Pans, this is a geodesic boundary and has two punctures. And then the second pair of Pans has two geodesic boundaries and the puncture, and then so on. So these surfaces, they have this geodesics have length, and we call them L1, L2, L3, and so on. And if you know a little bit about hyperbolic geometry, you know that when you glue two pairs of Pans along single geodesic, then there is also a twist parameter. So then basically this surface is determined by the ordered pairs lengths and the twist corresponding to this surface. So here, this one has twist T1. So if you like, you can measure the twist by taking orthogonal from this puncture to this surface from one side, and then from the other side, and then this is the twist. And we like to take normalized twist, so we divide this length by the length of geodesics. So the twist is really like of unit length. Anyways, these are the Fenchel-Nielsen coordinates. All right. So another popular surface is the infinite Loch Ness monster. So which looks like this, right? And here also you can choose Pan's decomposition into geodesic pairs of Pans. You can do these things. But then you have to add more cuffs, more geodesics here because the topology is more complicated, right? So for this surface, I would just call these that go to infinity L1, L2, L3, and so on. I will not even give name to these. And these which are cutting off the genus, I'll call them F1, F2, F3. And I will use the same name for the surface and for the geodesic and for its length. It's going to be the same, synonymous. So looking at this theorem, the natural question is which Fenchel-Nielsen coordinates satisfy that the Riemann surface R given by Ln and Tn is parabolic. So that was the question I asked, and I worked on with in a joint work with Grant, Jacobian, and Arabasmedjian. So we had sort of some results here. So we are kind of like, this is like maybe more classical stuff, and then these days people think more of these surfaces in terms of hyperbolic geometry and Fenchel-Nielsen coordinates and things like that. So I want to kind of connect this viewpoint with this theorem, and we're asking for sufficient conditions to achieve that. So we have the following theorem. So that's Basmedjian. Jacobian. And myself. So in the case when R is a fluid surface, R is a fluid, so we are in this picture here, then we said R is a fluid, or let's say, or R is this picture here, Loch Ness monster. So if we know that these cutoffs here are bounded by some fixed number m, so in this case the cutoffs are actually zero length because these are punctures, so we don't have to worry about it. But in the case of here, we have this cutoff. So if you know that, and if you know that the sum e to the minus ln over 2 is infinite, then the Riemann surface is in this class of being parabolic. So that was result. We also had results which including the twist, but maybe I don't have to say that right now. So looking at this thing, obvious observation is that if you take ln, which is 2 log n, then this condition is implied. So so regardless of what kind of twist we put here, if the length at most 2 log n, then this condition will imply that surface is parabolic, that geodesic flow is ergodic. So that's kind of a little bit interesting because you would think that if you increase the lengths, that gives more chances for geodesic flow to escape to infinity when it be ergodic. But this says that even if the lengths are going to infinity, but at this rate of at most 2 log n, the geodesic flow is still ergodic. So that's kind of one result. So these lengths can go to infinity at a logarithmic pace, and exactly has to be 2 log n. If you put here a bit more, if you put just like 2.1 log n, this condition will fail, but doesn't mean, since this is not equivalence, doesn't mean that the surface is not parabolic, but we will have a twist where that's not the case. So as long as you go beyond that, the twists at least kind of matter, if nothing else. So that's the type of theorems that we are proving. Another theorem so if you look at this surface, okay, it has these punctures which are kind of a way of going to infinity, which are very relatively tame, and it has one way of going to infinity which is kind of complicated. It has these pairs of pans, and here it has only one way of going to infinity, which is this pair of pans, right? So basically, these surfaces have only one non-simple infinite end. So similar to these, there are some results where you have finitely many ends, and they look kind of similar to this formula. There's no point of writing it, but they kind of have similar flavor that we can write down some kind of series, and in terms of the length, and this diverges, then the surface is parabolic. But then the case where it's significantly different is the case where you have counter set of ends. So so I'm drawing now, okay, so maybe I should have taken more overboard, but so if you look at this surface, that we all know this surface, right? Where you have this pairs of pans which are thickening of a Cantor tree. So the set of topological ends of this surface is a Cantor set, right? Right. So in that case, if you look at these pairs of pans, they still have the lengths and they have a twist. So here, this sufficient condition is quite different. So here, if you add the level n, then there is 2 to the n pairs of 2 to the n cuffs, right? And if we denote them by L n k, k goes from 1 up to 2 to the n, then the sufficient condition that we get is that same theorem, I guess, or same paper. If these lengths are all bounded from above by n over 2 to the n, then x is parabolic. So in this case, sort of these lengths, since we have sort of like we have counter set of ways of going to infinity. These lengths have to be quite a bit squeezed for surface to be parabolic, for geodesic flow to be ergodic. So that's kind of our sufficient condition. All right. So when we did this paper, one thing that we asked ourselves is this precise? In some sense. especially we were asking ourselves of this result, where we had to squeeze the lot. Is this really precise? And I think McMullen had the result which says that if these lengths are bounded from below by a positive constant, then x is not in this class of parabolic surfaces. So that's what he had before. And then when I talked to him about this result, then he said, yeah, Dragomir, I have this result, which says that, well, if these lengths are just bounded from below, so they could be all length 1, then the surface is not parabolic. So he had that, and then we kind of were asking ourselves what, there's a gap here, right? From being exponentially going to 0 and being bounded from below, there's a gap. And we were kind of, the question you ask is that thing true? So at this point, I'm going to switch to quadratic differentials. So the we filled it in, so I'll let you know in a second. So that's maybe motivation why I want to think about quadratic differentials. So there's this famous theorem by Hubbard and Mazur for compact Riemann surfaces. Basically, they said that if you take a holomorphic quadratic differential on a compact Riemann surface, and you can look at its horizontal measured foliation, and you can ask, well, which horizontal measured foliations are homotopic to the one which come from quadratic differentials? And their answer was, well, all of them. So the answer was that every homotopy class of measured foliations on S compact is realized, or let's say contains a horizontal foliation of a unique holomorphic quadratic differential. So, and since I like to think about infinite surfaces, I was kind of asking myself, well, what can be said for infinite surface? If you have some infinite surface, and you know that the space of measured foliation is really big, and the question is, which of them can be realized by horizontal foliations of holomorphic quadratic differentials? And well, there are many holomorphic quadratic differentials on infinite surfaces, but you have to restrict yourself to reasonable class. So I took the finite area as my class. So the question is, which measured foliation can be on infinite Riemann surface can be realized by finite area holomorphic quadratic differential. And by that I mean horizontal foliation, by horizontal foliations of finite area. Horizontal foliations of finite area. So what was known before is kind of also nice. What was known before, working on this thing, is that if you, it result due to René. Well, if you take, well, first, I guess, I don't know who did that first, but if you just take one, if you take one simple closed geodesic and you want to get a holomorphic quadratic differential on the infinite surface whose horizontal foliation has only has closed leaves homotopic to this geodesic, that's always possible to do on any infinite surface. If you have finitely many of them, as long as they are not intersecting, that's also possible to do. But here, of course, we can have infinitely many closed geodesics which don't intersect, and one would ask, well, can you realize those as being cylinders of some holomorphic quadratic differential? If many of them. So, and the runner gave a complete answer. So we assume that these alpha k's say disjoint simple closed geodesics, so that they don't intersect even in homotopy. And to this alpha case, if you choose B sub k some positive numbers, then if the sum, should I increase? Yeah. So if the sum k goes from 1 to infinity of these numbers B sub k squared over modulus of A sub k is finite, then there exists a phi holomorphic quadratic differential which realizes. These homotopy classes with heights of the cylinders B sub k. So it is if and only if. This direction is easy. And so this is basically the area condition. This is the area. But here, this A sub k, sort of in this theorem, A sub k is a choice. So for each, if this is alpha 1, alpha 2, and then maybe this one is alpha 3, then you choose some kind of annulus. And you just require that all these choices are not intersecting. So these A sub k's have to be non-intersecting. So that tells you that basically the type, the size of B sub k really depends on the geometry of the surface, right? Because how can you fit all of this together without intersecting? Will kind of inform you, given their models, will inform you how big B sub k can be. So that was known. All right. Okay, so I guess I can write here. So yeah, so then I introduce the definition of partial measured foliation. This definition was around. On Riemann surface R. So basically, you choose a bunch of open sets, or more generally, it could be some kind of measurable sets, which are subsets of the Riemann surface R, and you choose maps from these sets to the real numbers, which are say C1. Let's say C1 with tangent map being onto, and then you require that if two of them intersect, then the transition from one to the other chart is given very similar to what the transition is for the natural parameter of holomorphic quadratic differentials on surfaces, right? So it really mimics that one is plus or minus the other one plus the constant. So they are C1. They are C1 maps. And then you can define leaves of these partial measured foliations by just taking the inverse of a constant. Those are leaves. They are local leaves, and then you kind of keep extending. So that definition, I think it was around for a while. So I'll call this partial measured foliation F. And then if you have such a map, you can talk about the Dirichlet integral of such map, which is just the integral ui gradient vi squared, right? And then you will say that F is proper and integrable. First, proper if every partial leaf extends to an infinite leaf on your surface, such that both ends, in the universal cover, when you lift both ends, go to 2 points on the unit circle which are different from each other. So in other words, you can homotop that infinite leaf to actual simple geodesic, either closed or infinite. And integrable, you just require that when you sum over these charts, that this is a finite number. So you can talk about the Dirichlet integral of partial measured foliation F to be some kind of sum. Maybe you take partition of unity or something of this Dirichlet integrals to be finite. Okay, so horizontal foliation of finite area holomorphic quadratic differential satisfies these properties. And actually, the converse is also true. If you have a partial measured foliation, if satisfies these properties on an infinite surface, then there is a unique holomorphic quadratic differential whose leaves are homotopic to these leaves. And the measure is given by this measure. So that's my theorem. So the theorem so the theorem is that a partial measured foliation F on R is realized by a unique finite area holomorphic quadratic differential. And by this, I mean horizontal foliation. Horizontal foliation of if and only if the Dirichlet integral is finite. So that's the theorem on quadratic differential. So this kind of gives extension of the Hubbard-Maser result. And actually, this is true. Later on, I was able to extend this. This is true for any Riemann surface, which is given as a quotient of H by gamma, including when gamma is the identity map. So this is true for the case of the disk itself. So even in the disk itself, if you draw these partial foliations and you show that they have finite Dirichlet integral, then you can realize them by finite area holomorphic function on the disk. Integrable L1 holomorphic function on the disk. So immediate question, yeah. No, partial means that I don't have to cover the whole surface. I have wiggle room. So I don't even have to cover the whole surface. All I want is that these leaves are homotopic to hyperbolic geodesics. So they're nice leaves. And I don't have to cover the whole surface. It can be like subsurface. All I need to have some kind of integrability condition, and then I can tighten it and make it holomorphic.
There are also no singularity
Yeah, I don't have singularities here, so I don't worry about them. They will appear once you make them holomorphic. So I just, if you have singularity like this, you can just take this part, and this part, and don't even say anything here. You don't have to say anything. They will appear naturally when you stretch them. Now, this condition is not very explicit in terms of when you draw, let's say, even in the unit disk, when you start drawing some measured foliation or lamination and you put some weight, whether you can do that, whether you can realize it or not is not very explicit. What, for example, we know is in some discussion with Jacobian, we know that if you have a single geodesic with weight 1, you cannot realize that by finite area holomorphic differential because that differential will have infinite strip. So you cannot do that. Or if you have something of all the leaves having 1 point, and here non-zero measure, still you cannot realize that for the similar reason. So those are the obvious things that you cannot realize. So to be realizing something, even on unit disk, you have to work hard. You have to construct some measure. And I think a very nice question is characterize which measured geodesic laminations on the hyperbolic plane arise from finite area holomorphic quadratic differentials. So this is the classical Bergman space on the unit disk. And it is known that this map, which takes foliation, you can map it. You can map quadratic differential to your measured foliation, horizontal foliation. You can straighten this foliation to measured geodesic lamination. You can straighten these leaves to be a hyperbolic geodesic. And you get this kind of pictures, right? This or this. And it has some transverse measure. And a nice question is to figure out which of them appear. This map is 1-to-1. So this map from, if you call A of D, A of H, this Bergman space in the space of measured laminations on H, what is the image here? It could be an interesting question. I don't know the answer. I don't have even good examples. I know the existence, but it has to go through this condition. So what I can conclude from this theorem is, going back to the type problem, is that that surface R is parabolic. So now I'm going back to the realm of infinite surface. Surface R is parabolic if and only if almost every horizontal trajectory of every finite area holomorphic quadratic differential is recurrent. So, so to decide whether your surface is parabolic or not, you have to look maybe in the whole space of all finite area holomorphic differentials. But if almost every trajectory of every holomorphic differential is recurrent, then your surface is parabolic, geodesic flow is ergodic, and all these nice things. So that's the connection between finite area holomorphic differentials and this theorem. So in a sense, this gives you another line in this set of conditions, another line, right? So another equivalent condition. It comes back, doesn't leave every complex set, always comes back. Comes back to itself. Maybe to somewhere else, but at least to itself. Okay. So great. But also, this can answer this question. Okay, so it's very hard to check whether almost every horizontal trajectory of every holomorphic quadratic differential is recurrent, because you have to take all of them. That's kind of impossible. But if you take counterpositive, all you have to do is find one where you don't have recurrence for some positive set of measures, and then you're not parabolic. So that's used here. So maybe I can raise. So so the theorem, which is now due to my PhD student, Michael Pandazis, he finished and has a job. So you don't have to worry, okay? You don't have to worry, okay? But maybe if you give him more money or something, I don't know. So he said that, okay, he says, I can use that. I can use this picture. I can construct foliation here, which will have finite Dirichlet integral, and the leaves of these foliations will go to infinity. And he says, I can do that when this is almost not satisfied. So he says that if the lengths are greater than or equal n to some power r over 2 to the n. For a fixed r bigger than 1. So if fix one r, this is true for all n and for all k, but for one fixed r, then x is not parabolic. So he was able to use actual hyperbolic geometry of these pairs of bands, the lengths. He was constructing this foliation bit by bit and connecting them, making sure that connections are good enough that the measure from one band is equal to the measure of the other. They have to match. So there's is bigger, yeah. For anything of that for this is like, so if this is true for a fixed n and for all n and for all k. You can put some constant here, so maybe I should. Yeah, he constructs foliation and he uses this theorem, which says if you have this foliation, then you have holomorphic quadratic differential. So that I mean, when I had this theorem, I thought that's possible, and then he was actually able to, with some work. It's kind of fun. You're kind of constructing these foliations, and then you have obvious way to do when you have a rectangle, right? Then you take v of x, y is y, right? And the Dirichlet integral, so these are the leaves, and Dirichlet integral is the area. Right? But then he has this hyperbolic geometry where things get trickier. Even if you want to construct this one, you would have to kind of start doing a little bit of slanting. So there's some computation, and then you have to make sure that all of them match up, and then you have to add them. There is 2 to the n at one step. So it's kind of a nice, I think, construction. So yes. Okay. So maybe I can raise this part. So in addition to that one, let's see what else. Oh, okay. So obviously, I was interested even, so that question of figuring out what is the image is still kind of stuck in my mind. I don't know, because it's sort of like standard object, right? This Bergman space. And this would be another description or some connection with, so which is interesting. So I couldn't answer that, but I had another theorem here, which was working for the surfaces which look like this one here, like some infinite surfaces with infinite pairs of paths decomposition. So the theorem says that, so assume that R has bounded paths decomposition. Bounded means this, right? There's a lower bound and maybe an upper bound, right? So every cuff is between two positive constants. That's what bounded geodesic paths decomposition of Riemann surface are. Is, so we assume that. So let F has a bounded paths decomposition. That's assumption. So you'll call this paths decomposition alpha n, name for the cuffs. And in addition to that, we're going to have another family, beta n, which is minimal transverse family. Also of simple closure geodesics. So you would, I guess, start drawing things like this. So you want to have them, enough of them such that you break your surface into pieces which also kind of bounded, and every measured lamination or every measured foliation will have to intersect some of them. Now, they cannot go and sneak out and not intersect. They have to intersect one family and the other, unless they do some kind of spiraling like that. So you have this kind of, you break your surface in addition to having pair of pants, you chop these pairs of pants by these green curves, so you don't have a geometry. Everything is simply connected, but you do it like not too much. So under this condition, then if you have mu, so mu is this one, right? Mu is some measured geodesic lamination, and the question is, when can this measured geodesic lamination be realized in the homotopy by holomorphic quadratic differential of finite area? So mu is a measured lamination. On R is realized by finite area holomorphic quadratic differential if and only if the sum n goes from 1 to infinity, the intersection number between the curves alpha n and measured lamination mu squared plus intersection between beta n and measured lamination mu squared is finite. So this is looks sort of like some L2 condition. And at least on the bounded geometry where all these curves are bounded length, that's true. So I could at least answer in this situation what is exactly the image. So I would hopefully, my hope is to get some kind of satisfying answer for maybe for the hyperbolic plane. Like if someone gives you measured lamination, you can say just in terms of this measured lamination, nothing else, whether it can be realized or not. So that's the type of questions that appear here. So I don't have much time, right? How much I have? Half a minute. Okay. Okay. I guess I'll stop then.